Hello again, folks. This is Mr. Brewer here, and bring a lesson today on the topic of matter and some of the types of matter, maybe a little bit of language that relates to the actual topic area. So we can see here's some very specific goals. What this lesson is going to cover. I'm not going to read those goals to you, but know that you can refer back to these as need be. You should have access to these as part of your notes as an attachment in your classroom as well. Okay, so let us get underway about what chemistry is really supposed to be about. It really does concern itself with anything that's made of particles, which is kind of what we think of matter as being. And particles can do interesting things to undergo changes. So sometimes those particles can do what we call freeze. Sometimes those particles do what we call chemically react. Well, freezing means something different happens to the particles than chemically react. And the essence of some of the information in this unit will get at the essence of how that might be different. Sometimes when something does undergo a change, there's evidence of that change. So it might be like it gives off a specific color of light, or we feel heat energy. Sometimes there's even evidence that something has happened with what we would call the electrons. And the electrons will become a very, very, very important particle that relates to key ideas in chemistry later in this course. So I at least wanted to mention it early on. So when we think about what matter is, I like to think about the concept. Our textbook definition says that it's anything that has a mass or a volume, and as a result, it's made of particles. So because it's made of particles, it can occur in what we would call different states. And one thing that we'll look at is what is the cause of solid, liquid, and gas states, and how might plasma be different than that? That won't be part of today's lesson, but that'll be coming soon. I think a good way to grasp what forms of matter are is to understand what they're not. So things that are not matter would be energy forms, things like light. Light's not made of particles. Light, you can't shine a light into a container and measure how much space it occupies. You can't shine light on a scale and see a reflection of how heavy light is. So heat energy, again, not a form of matter, not generally thought of as being made of particles. Sound, right? It's kind of energy that moves through gases in the atmosphere. And as those gases vibrate, it transfers that energy from one place to the next. So matter is generally anything that has measurable qualities like mass and volume. So the measuring of mass or volume relates to some information I think we should have in our background. So volume is what we would call the three-dimensional space that when we put particles in a container, they occupy space, or the particles themselves occupy some space, like the eraser has a very specific volume based on its dimensions of length, width, and height. How much three-dimensional space does it take up? Well, that could be measured. So when we talk about liquids, there are tools for measuring liquid volumes, and some of those tools we're familiar with. Some of them we might not be as familiar with. So one of them is called graduated cylinders. Cylinders of all various sizes. They give us very versatile, a good range of volume for measurement. This one can range anywhere from 0 to 10. This guy anywhere from 0 to 50. We can get larger ones that could go all the way up to 1,000. You can even buy some maybe like 2,000. So something called a pipette. Pipettes are generally for very small volumes. In fact, this one is only useful to measure 5 milliliters. So that's all you can measure is 5 milliliters. If you fill it all the way to this line where my finger is, you get a very exact measurement of 5 milliliters, much more exact than a graduated cylinder. Other pipettes can measure various volumes, right? A range of volumes. Okay, so pipettes, generally they're different because they measure small volume, but super accurate tools. Some people like to think of beakers as being measuring tools. They're really not. They're not marked with the level of exact that we need. We can see here the marks. It ranges from like 250 to 275 to 300. So it's marked by like every 25 milliliters. That's a rather poor measuring tool. So When we talk about the measurement of solids, what we use generally are the dimensions, length, width, and height, or if it's a cylinder, right, pi r squared, r relates to the radius, right, times the height, how tall it stands. Put together those dimensions, we end up with a volume in usually cubic units, cubic centimeters, cubic inches, so on and so forth. So volume units, I would like you to be familiar with units of volume, things like milliliters, liters, cubic centimeters, gallons, quarts, cubic inches. So if it's a cubic unit, it's a volume unit, or if it sounds like a container size, teaspoon, cup, pint, gallon, liter, it's a volume unit. You should be aware of that. It'll help you be more successful with future learning. So if we were going to measure a solid volume, another way that we could use that wouldn't use the dimensions would be what I said here called displacement. We take a solid object, we immerse the solid object in a cylinder that already has some water in it. That object displaces the amount of water equal to its volume. So here we got SpongeBob as a volume of about 2 milliliters, right? Because he has displaced 2 milliliters of volume by being inside the cylinder. So graduated cylinders, right, pipettes, right, they're all tools that help, beakers, they're all tools that somehow reflect volume. And for solids, we generally use the dimensions, things like if it were a cube, length times width times height, or a rectangular prism, or if it were a cylinder, pi r squared times height, we end up with cubic units when we make those style calculations. So volume is a reflection of how much space particles take up. Mass, on the other hand, I like to think about as mass as what Patrick Starfish says, particles. So mass is how many particles generally a form of matter is made up of. So the total amount of matter, I would rather call it the total number of particles. And it's a reflection of how heavy something is. Usually units like kilograms, grams, pounds, ounces are reflections of mass. If we're going to talk about particles, there's basically two kinds, atoms. Atoms are single units. They're not bonded with other units, not bonded with other kinds of atoms. As soon as we bond atoms with other kinds of atoms, then we're talking about molecules. So here we got a single atom of aluminum compared to a single atom of lead. Well, they're both atoms. They're different because lead atoms are heavier than aluminum because lead is made up of a different kind of a nucleus than aluminum. So when we have two or more atoms joined together by what we call a chemical bond, it usually represents what we call a compound. It could represent what we call a diatomic element. When there's two or more atoms of the same element that have been bonded. So that idea is a little unique. There are 7 elements that do this. There's a nice, easy way to remember which 7 elements do it. I like to call them the genuine elements. They end in gen or ine, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So we call those the genuine elements. There are 7 of them. Oddly enough, or interestingly enough, they sort of make the shape of a 7 on the periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and over here on the left, hydrogen. So they sort of make the shape of a 7, but they end in gen or ine. They're the 7 elements that we would call diatomic. They make molecules. They don't exist as single units that we call atoms. So the next topic area we want to touch on relates to the different types of matter that we have. We have either matter that is pure, we call those substances, or matter that is mixed. There's obviously more than one chemical mixed together. Pure means one of two things. It is either made of just one element or it's made of some fixed combination of elements. So those are your two possibilities for pure. It's made of one element, it's an element on the periodic table, or it's made of a fixed combination of elements like glucose, C6H12O6, has a well-defined formula. All glucose is C6H12O6. Sometimes chemicals don't have well-defined formulas. Well, sodium chloride does. So there's a chemical called ink. There's no well-defined formula for ink. Ink can be made various colors, various types. This kind of ink is called dry erase, so it's not permanent. There are more permanent forms of ink. So ink, we know, is not a substance because it doesn't have a well-defined formula. And you also know ink is not one of the chemical elements. You could look on the periodic table and you'd never find ink on there. So ink, however, is one of the types of what we would call mixtures. So, and what we're going to do is take a look at the essence of how we understand that there are also two different types of mixtures. So here we're looking at, obviously, multiple chemicals inside all these layers, this top layer, a middle layer, and then a bottom layer. So we know that this is not very well mixed. It's not mixed in a nice uniform way. We would call that heterogeneous. Typically, ink is mixed in a nice uniform way. So when we draw, all the ink that we draw onto the paper looks about the same. So we would call that homogeneous mixed. When things are heterogeneous mixed, we can sometimes see the individual chemicals. We call those the phases of it, right? The layering or the phases. So if we had rubbing alcohol, 70% rubbing alcohol, right? The other 30% of this is water. If we take this and we put this water in a vessel that we call a beaker. Where's my beaker? I know I have a beaker here somewhere. There it is. We pour it in there. 70% of this chemical is rubbing alcohol, isopropyl alcohol. The other 30% is water. Look at that. I don't see any layers in there. So that means this mixed up very well, nice and uniformly. And that we would call this a homogeneous mixture as a result. So when we know there's more than one chemical present, but it's mixed really, really well uniformly, we call it homogeneous. When we know there's more than one chemical present, but it's poorly mixed, not uniformly mixed, we know that's called heterogeneous mixture. There is a synonym for a homogeneous mixture. The synonym is called a solution. Okay. So moving forward, if we were going to classify the different kinds of matter, one way to do it would be to worry about, well, do the particles suggest that it looks or appears to be uniform? That would be one way to do it. So up on top here, that I'm just making a little box around, these are not completely uniform properties right here, right? There's this big glob of red area here. It's not completely uniform. So we know that's mixed. Here it's mixed kind of well. A blue molecule, a red, a blue, a red, a blue, a red. So here we got some uniformity, but there's two different particles. So that's kind of like our rubbing alcohol. We know there's two chemicals present, right? But it's mixed very well, mixed in a very uniform way. So we would call that a solution, right? One of the reasons we know that it's called a solution, well, it doesn't have a definite chemical symbol or a formula, right? Rubbing alcohol mixed with water actually has two chemicals in it. So down here below where we have the element, right, it has a fixed composition. It's always this red molecule, always this red molecule. Down here, the molecule is made of two different elements, a white and a red. So here's what we call an element because it's made of the same particle each time the molecule. Here's what we call a compound because the molecule is not made of the same element, but it has a fixed ratio, 2 white for 1 red. So a well-defined chemical formula makes something pure that we would call a substance. Okay, moving forward, we'll go back and quickly review the two pure forms of matter. One's called the element, right? They're the simplest forms of matter. They can't be broken down unless we change the identity. If we split an atom, it's no longer the same element. It's some fragment of what it used to be. or fragments, I should say. Some elements need to be diatomic, like oxygen and chlorine. We said there's 7 elements, the genuine, oxygen, nitrogen, hydrogen, fluorine, chlorine, bromine, iodine. However, most elements exist in the atom form, like aluminum and lead. So the genuine elements like oxygen and chlorine end in gen or ine, they're unique. So usually the individual particles of elements, we call them atoms, things like aluminum or lead. Pure forms of matter. Oxygen's pure, chlorine's pure, aluminum's pure, lead is pure. There's no other kind of particle mixed with the oxygen molecules, so on and so forth. So the other pure form of matter, what we would know as compounds. Compounds, really the difference between elements and compounds really just has to do with the fact that compounds are some combination of at least 2 different elements, and it's a fixed ratio. So fixed ratio like a chemical formula, nitrogen oxide, NO, water, H2O. So the ratio of H's and O's is always constant or fixed. It has a well-defined formula is the way that I like to describe that. So the individual particles of compounds is typically called molecules. We're going to learn later in the year that's not exactly the truth, but for now I think we can stick with that. When we take a look at the mixed forms of matter, the mixed forms of matter are either what we would call homogeneous. It appears to be uniformly mixed, yet we know there's more than one substance in it. Maybe something like liquid hand soap. We know there's a whole laundry list of ingredients in here, but look at how it looks. It looks pretty uniform throughout. So we know it has multiple substances, but no well-defined chemical formula, because here's another liquid hand soap, right? It has kind of a greenish color. If all liquid hand soap had the same chemical formula, it would all look the same. Homogeneous would be when a sample of matter has more than one phase, similar to this, right? Indicating that there's more than one substance present. So more than one substance present comes from the fact that we know it's made of multiple kinds of particles because there's good visible evidence in the case of most heterogeneous mixed chemicals. So something like Kool-Aid, generally Kool-Aid would be homogeneous mix. You'd want one sip of Kool-Aid to taste like the other, so you'd have to mix it very homogeneously to make that happen. Here we got a red wine vinegar Italian dressing, obviously heterogeneous mixed. Here we have sand. Sand comes in various colors, right? It's from the rock material that's eroded over the years. There's sands that are white in color. There's sands that are black in color, sands that are pink. The sands that we tend to see in the New Jersey regions or on New Jersey beaches tend to be kind of a brownish. But no 2 samples of this sand are going to look identical. So we know it's not well mixed. It's not uniformly mixed, I should say. And then maybe something like glass. Glass comes in all these different colors: red glass, brown glass, clear glass, blue glass. We know that glass doesn't have a well-defined formula. It's a mixture. That's why. So as a result, we do try to make glass so that it has uniformity, so that one sample of the glass looks identical to the other, yet it's made of all these different chemical substances mixed together. So if we were looking at pure versus mixed, right? We look for how many different kinds of particles is it made up of? Well, letter A, there's just one kind of particle that we would describe as an atom, and A represents our pure form called an element. B, our pure form, but now there are multiple atoms bonded together, but in a fixed ratio, 2-to-1 ratio, makes it a compound. Letter C, not pure. 2 different kinds of particles present. There's this atom here and this molecule. But look how it's mixed. It's blended nice and uniformly. So we would probably call those particles arranged homogeneously. And then finally, our substance, which happens to be an element, our diatomic form, 2 of the same element bonded together. So we can wrap up with just a few examples here of classifying, and let's do that right here. So I'll pause the slide so we can write on it, and then we'll come right back and we'll briefly speak about each. Okay, so here we're looking at some combination of a white and a blue, and it makes the same molecule each time we see it. That makes it pure. Well, the ratio is 1 white for 1 blue, which means it has a well-defined formula. So this is a substance. It's pure, and it represents the kind of substance that we know as a compound, because there's more than one element bonded together in a fixed ratio, a 1-to-1 ratio. Alongside of it, over on the right here, now we have just one kind of atom present, right? So again, it's pure, it's a substance, but now it's represented by the type of chemical that we would call an element. On the bottom, we kind of this slide, we kind of cut it in half. On the bottom are examples of things that are mixed. So here there are 2 different kinds of atoms, right? We're not going to call this a molecule because they're not bonded together. So we know it is mixed, but look at how it's mixed. It's mixed in a nice uniform style arrangement. It's almost like the pink and the white alternate. And we would call that homogeneous. There's a repeating pattern, and it makes it appear like it has uniformity when we look at it. It makes it appear like it's one chemical substance, similar to like what hand soap would do. It's mixed nice and uniformly. Alongside that, wow, look at all these different chemical substances we have. We got one here, one here, one here, and one here. There's 4 chemicals mixed together there. So we know that is a mixture. It's certainly not pure. And look at how it's mixed. It's mixed in a rather random arrangement. There's no uniformity to the pattern in any way, and we would call that heterogeneous. And as a result, maybe that looks similar to what we would see here, where we sort of have layers. So that wraps up the introduction to matter, types of matter, and classifying. So until the next time, I'll talk to you soon. This is Mr. Brewer. Have a great day.